So, let's see. I I deleted a couple of the pre-lecture videos today, which was fun. So I re-uploaded those three that I deleted. The last one just finished re-uploading and it's processing now. So those are back. They're not the ones that were for today. I think they were the ones that were for yesterday. So if you were looking for those and you saw that there was a spot where it used to be that said video deleted, that was my fault. I fixed it and I won't do it again. Let's see. Oh, in mastering physics, there are two things I wanted to, not mastering, that's what I used for the other course. In WebAssign, there are two things I wanted to mention. One is that you have several submissions that do not dock your grade. All right, I think it's 8. And after 8 submissions, you start losing 5% for each subsequent guess. Because if you've done 8 times, after that, you're guessing. No, not necessarily. But I would suggest if you enter something and it tells you it's wrong, don't enter it again. That's tempting to say, no, I feel like I'm right. Check it again. Like, no, it's a computer. It's going to continue to tell you you're wrong. So things like when you enter something in scientific notation and you enter x 10 caret some number, that's not the syntax that it wants, and that's just learning how the system works. So what it wants is an E and then the number. Let me do this. Yes. Work. Please work. Sorry, I'm having technical difficulties. This was working. How else do I share that? Give me one more second here. What was that? I'll just reopen it. Let me mention while I'm doing this. There are also quizzes for our course, right? I think the first quiz is due today or tomorrow, maybe tomorrow. They're all due at midnight. They're all conceptual questions, right? And they are open note, open book. So feel free to consult those resources. Okay, so here's what I'm talking about. If you wanted to enter 52.3 times 10 to the minus 7, you would need to enter 52.3 E minus 7. All right, so the E means times 10 to the. Does that make sense? Where did you guys go? Oh, there you are. Okay. So let me ask before I launch into the rest of lecture. Are there questions about anything? Let's go away for a second.
Yeah, I kind of have a question.
Yeah.
It's just been a while since I've had trig, but like, when are you using arcsine and like arctangent? Like, I was confused in your videos when you like decided to pull that out.
Okay. An arcsine and an arctangent, those are just the inverse functions. Let me screen share again. All right, so when we say we've got a triangle, build it this way, that's like, let's make it a 3, 4, 5 triangle, right? And I want to know this angle. So I can do sine of theta, right? Sine is so, right? So that's opposite over hypotenuse, so that's 3 over 5. So to get to this theta, I need the arc sine. So it's like an unsine. Does that make sense? So to unsine, I do arc sine. And on your calculator, on my calculator, it's a shift on sine, or maybe I've got a green shift and a yellow shift, I think. On your calculator, it may be something else. Cody, does that answer your question?
Yeah. So like, why would you untheta it, or what did you say? Unsign or
Unsign, yeah. Because how else do you get to theta, right? Because you can do 3/5, that's a number. But if I want to get what angle that is, I need some way to get rid of sine, or to unsign.
Okay.
It's similar to like an unsquare root, right? If I said the square root of x is 25, no, that's probably what I don't want to do. What I want to do is
so it's kind of like you're almost dividing, instead of like you're just flipping sine on the other side to sine of arc sine.
Yep.
I got you.
How do I undo sine, right? Just like how do I undo a square root when I got to square it? There's just not a this is just a function that undoes sine, the arc sine.
Okay.
Cool. Yeah, other questions? No. Okay. Okay, cool. So what you hopefully watched before today's lecture was that list is, I've got 3 monitors and it's not actually enough. And I've got an iPad in front of me. Here, yeah, hopefully you watched the vectors video, the motion on an incline plane video, and projectile motion. Projectile motion didn't show up until a little later today because of some of my video issues, but hopefully you're able to watch that. And we will work some problems for, particularly for the last two, motion on a slope and projectile motion. But let's talk about those for a minute. So there are 2 ways. I'm going to screen share again. There are 2 ways, at least, to add vectors, right? So vectors are just arrows. So there's a vector. I don't want to use X, but I'm tired of using A. Let's use C and here, D. Right? And I could ask, what is the vector sum of C and D? And I could even give these guys sizes, right? So if this is 5 and this is 3, the answer is not going to have a length in this case of 8. Right? Why wouldn't it have a length of 8? Well, because C and D don't point in the same direction. If they did, if they happened to point the same way, then the answer would be 8. But in this case, again, the way we can add these is tip to tail. So if I take this vector and move it over right here, and then maybe make the lengths go away because they're kind of in the way. The answer to this addition problem is that vector right there, right? That's C plus D. We could call it E because I know the alphabet. So the tip to tail method, and I think I showed in the video that tip to tail works either way. You can add C to D or you can add D to C. This is easy to visualize for displacements. If I walk the vector C and then walk the vector D, my total displacement is E, right? But it's the same is true for, I think I mentioned it in the video, forces. Any vector actually adds this way. It's the same for momenta. It's the same for velocities. Yeah, there are lots of forces, there are lots of vectors we can talk about here. But that vector E is, it's not super precise, right? Even if I know the magnitude and direction of C and D both very precisely. If I just draw the picture, the precision of my answer depends on how well I can draw. So I'm in trouble if that's the only way I can get the answer, because I don't draw very well. But the other way we can add these is we can break C and D into components, right? So any vector can be represented as bits that point along any axes. So I could say, let's talk about, no, let's not do that at all. Don't do that. Let's say I've got a vector that looks like this, right? Let's call it B. And I could say, all right, let's decompose that vector into components. Well, in order to get components out of this, I need to know what are my axes, what are my X and Y axes. Usually we make Y straight up and down and X right and left. You don't have to. If you watch the second video, there actually are good reasons to tilt axes. So if I know the length of B, let's call the magnitude B, and the direction here is that. Sometimes you could use absolute values of the vector B to mean magnitude. Let me mention this. Magnitude is always positive, and you see there's a part of B that is negative, right? It points to the right, which is a positive direction, but down, which is a negative direction. But the magnitude of a vector is always positive, right? It's just saying how big is it. It's always positive. So I've got the magnitude, and then the direction is that theta. And I could either call that a negative angle, or I could say it's some angle below the positive x-axis. But what I'm talking about is, let's break that into components. So I want an x component, which points here. So that's b sub x, and a y component, which points here, b sub y. Right, so you can SOHCAHTOA this guy, because SOHCAHTOA is now a verb. And you can say bx must be b times cosine theta, and by must be b times sine theta. Right, and that's generally how this works. So you have to make sure that your angle is defined to an x-axis. Again, I did an example in one of the videos that swaps these. The x and y components of the acceleration were actually reversed, the sine and the cosine reversed, and that had to do with how that angle was defined. But if you just do SOHCAHTOA every time, you'll be fine, right? So the adjacent theta is adjacent to the x component, so it's going to give me a cosine, and it's opposite to the y component. Okay, questions so far? Just kind of just a review of that first video. Okay. So if I were thinking components for this guy, I'm not going to do, I'm not going to do numbers for this. I just want to write this equation. So if I have C and D added to get me E, to get the components of E sub x would just be the sum of the components of the things that are going into that sum, right? And E sub y is C sub y plus D sub y. So then I would just break C and D into x and y components and add those components together. So I don't have an example lined up for that right now, because we did, it says to do the example here, but I think, oh, I think I did that example in the, yeah, I did that example in the video. I know it was a little bit of a longer video, but I think it was worthwhile for that to be right after that discussion. Okay, if there aren't any questions, I'll move on to the next idea, which is this, let's see, this idea. So in the pre-lecture video for motion on an incline, I gave this example of a skier traveling down a slope. And it mentioned that this is really a one-dimensional problem masquerading as a two-dimensional problem, right? Maybe that's not a fair way to say it, but that's how I'm going to say it. If you tilt your axes, right, if you think of the x direction as along the slope and the y direction as perpendicular to the slope, there's only motion in one of those two directions, right? There is no motion in the y direction, so I don't even have to think about it, really. So it's just a one-dimensional problem, a kinematics question, really, where the acceleration is a little less than g, right? So that's the tricky part, is I have to figure out what the size of acceleration is, or really what part of the acceleration causes this skier to accelerate down the slope. And it turned out it was this, what's a good color here? It was the x component right here, right? A sub x is what accelerates him down the slope. And then it's just a kinematics question with a smaller acceleration. So I want to do another problem like that. All right, I want to do example number 4. So a box rests at the bottom of a frictionless slide. The slide is 10 meters long and makes a 30-degree angle with the ground. We're going to give the box a shove, right? We're going to push it up the ramp. Not so it's a shove, not a push. What I mean is you push it and then let it just slide up the ramp under the action of just gravity, right? So the question is, how fast can I set that moving at the bottom without it going off the top? Right, so let's draw that picture. I think there's a specific way I want to draw it. Yeah. So what does a slide look like? Oh yeah, that's perfect. More or less. There, now it's perfect. So this is my slide. All right, partially because I want this slide to be a straight line motion, right? So maybe this is a boring slide. So the angle here is 30 degrees. The slide is 10 meters long, and I intend for that to be the ramp length, right? There's my 10 meters. And we have this box at the bottom of the slide. So the box is down here. And we're going to give it a shove. We're going to give it some V initial, right? And ultimately, we want it to travel up the ramp and to stop at the end of the ramp, right? So I want V final to be 0. And the question is, find V initial such that it travels the 10 meters and just stops at the end. Does the problem set up here make sense, guys? Good, good, okay. Let me check the chat, make sure. There's a chat. I clicked it, but it didn't go anywhere. Okay, fine. Okay. So, so again, if we set up axes this way, here's X and here's Y, the motion here is in both the X and Y direction. But if we take that and tilt it, I doubt I can do this, but I'm gonna try it. Oh, okay, fine. The magic of the pencil has broken. It's fine. So I'm going to call this X and this Y. So let me say this. There's nothing wrong with setting up axes that look like this, but there's something right about setting up the tilted axes. There's a benefit we get that makes the math easier, right? Because then this is a 1D problem. So the answer to the problem can't depend on what we choose our axes to be, but the difficulty of the problem might. And that's what we're doing here, is trying to toy with the difficulty of the problem. So we have some given information. This is a kinematics problem. Do you see that? It's a constant acceleration problem. And we have a set of equations that help us with that. The kinematic equations, what I really want are the equation sheets here. The kinematic equations are not circled here, but they're these guys. Come on. Let's make some of the other notation go away. The kinematic equations are these three equations, right? And we could write down what we know and what we're looking for. It's useful here to have this sitting next to your, next to what you're looking at, maybe on a different screen. I don't have a way to split this screen easily, so we're just going to look at this and then remember what we're looking for. So what were we given? I know delta x, or x final, right? That's 10 meters. I know v final is 0, right? I want to get to the top of the ramp and not be moving. I don't know a time. And I'm looking for v initial. So the last equation doesn't include time, but it does include an acceleration that we don't know, right? And I'm looking for v initial. There's v initial. I could do one more color and say acceleration, right? So I'm going to need to find a first, and then I can find v initial. You guys buy that? The good news is this acceleration is acceleration due to gravity. It's just part of the acceleration due to gravity. So let's go back here, here, here. Too far. Okay. So the equation that we had there was v final squared equals v initial squared plus 2a delta x. All right, so we just said v initial is 0. Delta x is 10. We're going up the ramp 10 meters. V initial is what we're solving for. No. V final is 0. My bad, that matters. Oh, come on. Okay. All right, so I need that acceleration. So let's draw some axes here. I'm gonna draw the axes a little bigger and almost correctly tilted. There's X, there's Y, and use a different color. Blue is fine. So G is the acceleration due to gravity, right? And part of G points down the ramp, G sub X, I guess, and part of G points into the ramp, G sub Y. So G sub Y, I don't care about in this specific problem. In the next chapter, I might. And in fact, we're going to attribute this acceleration to a force, and then that force is something I'm actually going to care about. G sub Y is what's holding the box against the slide, right? But I don't care about that in this problem. So all I really need is G sub X. And again, the trick here is to figure out where is theta. One of these two angles is theta. Now I did this reasoning already in the problem on the video. So maybe instead of going through that reasoning again right now, because I want to have enough time to do the projectile motion question, I'll just tell you. The angle that is theta is, oh, now I'm going to argue it to myself. It's this one. Right? Again, if you imagine theta going to 0, Gy becomes G and Gx becomes nothing. That's the point. So here, now that we've got this set up, gx looks like it's an opposite. So g sub x is going to be g sine theta, or 9.8 times sine of 30. If you do that math, you get 4.9 meters per second squared. And now we can plug into that kinematic equation. Questions? Okay. So there's one last detail that I need to manage, and that is this. The direction of g sub x is negative, right? So I need to make sure that I put a negative sign in here, because if I don't, the math isn't going to work out. All right. In the previous problem, if I scroll up, gravity was still causing acceleration down the ramp, but that a sub x was positive, and that was just a function of how I set up my axes, right? I was calling down the ramp positive last time, and so that 4.63 was positive. This time I'm calling down the ramp negative, right? Or I'm calling up the ramp positive. So g changes signs. Doesn't matter what you call the positive or negative direction, you just need to be consistent with everything that you define relative to those axes after that. Okay, so we're ready to just plug in. Come on. That's terrible. I can do better. V final squared equals V initial squared plus 2a delta x. V final was 0. V initial is what we're solving for, plus 2 times negative 4.9 meters per second squared times delta x. It should be pointed out here that delta x also has a sign, but we're going in the positive x direction, right? We're starting at the bottom at the origin. We're going up the ramp, which is positive. So that really is a positive 10 meters. Okay, and it looks like I got the signs right, because when I multiply this out, I'm going to get a negative number. I add it to the other side and I square root, and that's going to give me something that is real. So I get for my answer something. Where are you? 9.9 meters per second. Okay. Questions about that problem? Again, it's pretty much just a kinematics question on an incline. I'm trying to point out a couple basic physics ideas here. Again, that sign is something you have to keep track of, and it doesn't matter whether you call up the ramp or down the ramp positive. It's just as long as you're consistent afterward. Okay.
So I do have a question real quick.
Yeah, please.
So with those like kinematics equations, like you showed us, there's like 3 different ones.
Yep.
Are you basically like taking like whatever of those 3 you had the most data for, you just use that one and just like plug everything in?
More or less.
Okay.
Yeah, because actually I could have used the first 2. I could have used the second one and solved for time, and then plugged into the first one to find the same answer I got, just using one equation. So there's no like single path to the right answer. But again, solving for time as an intermediate step is just an extra step. So if you remember, we got the third equation by solving one of the equations for time and plugging into the other one. So,
okay.
Cool, yeah? But what other questions do you guys have?
Yeah, so can you explain how you found theta from when you made like the axes and coordination with the triangle that you made? Because I'm still confused on how that happened.
Yes, I can. Not that one here. So are you asking, how did I know this was theta instead of this?
Yeah.
Okay. So here's what I do. I imagine the extreme case. So I just need like blank space here. Great. So in the extreme case, I could say, let's say it's a really shallow slope. So theta is very small. So then when I draw my axes, the horizontal is a little more horizontal. Make that a little. So there's X. There's Y. But G still points straight down. Right? And now I can look at those and say, which one of these angles is the small angle? Well, clearly it's this side. So that side must be theta. Does that make sense? So
yeah.
if you're comfortable with the idea that one of those two has to be theta, the extreme case lets you pick which one it is.
Okay.
Cool. That's a great question. What other questions do you guys have? Okay. Okay. So the last idea I want to talk about is projectile motion. And I did, again, post a video about this. The idea, yeah, this is good enough. So this is the work for the problem that I posted previously. The idea is an object can move in both X and Y at the same time. In fact, most of us do. And when that object is under the action of just gravity, in the Y direction, it follows the free fall equations. And in the X direction, it's just a constant velocity. So those two things together give us projectile motion. Projectile motion is always a parabola or maybe part of a parabola. And the trick here, where did I put those equations? Here, I put them under, not there, not there. Let's see. Can I sort them by recently? No, I can't. It was here, yeah. So in the Y direction, we have the free fall equations. In the X direction, we have the constant velocity equation. The notation here is from the problem I was solving. Just make those two things go away. And the trick really is that you have an initial velocity, and that initial velocity sometimes has X and Y components. So you cannot plug the off-axis velocity into either one of these equations. Right? The Y direction equations require Y direction information, and the X direction equation requires X direction information. So the variable that they have in common is time, right? Time doesn't have a direction, so it shows up in both sets of equations. So I think what I want to do is work one more problem, and that would be problem 7. This is 6. 6 is fun. 6 is the same as problem 5, only on a horse. All you really do is you add the horse's speed to the velocity's X direction. Sorry, to the arrow's X direction velocity. Okay, example 7. This is a good problem. A cargo plane travels at 200 miles per hour and it drops a package. If the package lands 245 meters from its original location in the X direction, not like at an angle, how high is the plane flying, and with what speed does the package hit the ground? Okay, so we need to draw a picture, which means I need to draw a plane. How do you draw a plane? How do you draw a plane? I don't know. Like it's got to have a nose. So what does his nose look like? Oh, perfect. And if there's some wings, and there's a wing. Oh no, that's a terrible wing. And there's the back of that's a plane, more or less. And the plane is flying this way at 200 miles per hour. And I already know I'm going to have to convert that to SI units. So let me just say, instead of doing it on the fly, well, maybe I'll do it on the fly. See if I have those conversion vectors. No, I want the eraser. No, still not an eraser. There. Okay, so I'm going to multiply by 1006. That's not a 6. 1,609. There are that many kilometers in, no, it's 1.609 kilometers per mile. Let's make that, so if I put a decimal here, oh no, the decimal makes it kilometers. Okay. I'm trying to do too many things at once. It's 1,609. Yeah.
Quick, the free trial version thing is back up on the, okay.
I moved it. Thank you for telling me.
No
Because
problem.
it doesn't show up on the iPad. It just shows up on the screen over here. Maybe I'll look into how much that costs and charge the department for it. I mean, there's a way to do it like kosher through the through Zoom, but it won't work for me for some reason. Okay, so these two conversion factors together should convert this to meters per second, and it's 89.4 meters per second. I've got 3 minutes to solve the rest of this. We'll make it happen. Okay, so we're dropping a package. So what does a package look like? It's a box. Sure, there's my box. And the box starts with the same initial velocity as the plane. Does that make sense? One of the like stereotypical conceptual questions for physics is, what is the path of this box, right? Does it do this? Does it do this? Does it go backwards? So you could label those as like 1, 2, 3, 4, and 5, right? Which path does this follow? Well, the answer is 5. And that's because the initial velocity of this package is to the right, right? Imagine like if you throw some, well, okay, if we're ignoring air, it's going to do this. If we include air resistance, it's going to slow down immediately, but it's still going to go forward, right? When you throw something out your car window, which you don't do because that would be irresponsible, but when you do, it doesn't go backwards, right? It goes backwards relative to you because of the air outside, but it's actually still going forward, right? And if you watch someone throw something out of their car from outside the car, it bounces in the direction that the car was going. So 5 is the path that this is going to take. So this is half of a parabola for projectile motion. So let me think about this. So here's what I'm going to suggest you do. Take a look at the rest of this solution. So the solutions to the discussion problems are posted now. The solutions to the lecture handouts are also posted to Canvas. So take a look at the rest of that, the solution for this problem. It's pretty, I wrote a lot on it, or at least I numbered all of my steps, so hopefully you can follow it. So what I'll ask maybe is when we start our next class tomorrow, I'll ask if there are questions about this problem, and then we'll move forward. So I'll ask now because we've got probably 60 seconds left. What questions do you have, aside from what's the answer to this?
Hey, Professor.
Yeah.
Do we have to buy the Cengage thing on WebAssign? Or like, because it says I have a trial version, but.
Oh, yes. Yeah, you will.
Okay.
Cool.
Thank you.
You betcha. Other questions? All right. So, so yeah, I guess the next thing will be, some of you have lab right after class now, and the rest of you will have either had lab before this or will have lab with me tomorrow. So I'll see some of you in lab, and the rest of you can't see me. Maybe you can see me now. The rest of you I'll see in lecture. So thanks, guys.